Welcome back. In our last lecture, we discussed on STM imaging, different modes of operation like constant height mode, constant current mode, and how to get the image. A little bit about imaging processing, and there are different artifacts in the image. So, after considering the imaging, we are going to move towards spectroscopic scanning tunneling spectroscopy. So, the same machine, same technique can be utilized for getting electronic structures of the material or further information about the material surface, particularly the surface. So, today lecture we will discuss on how to measure local density of states of the surface and also the band gap of the sample or surface at the surface, including for those nanomaterials. In broadly, the STM can be utilized for imaging that we have discussed in last lecture, either constant current mode or constant height mode. We can also do spectroscopy study, that is what we will discuss today. There is also manipulation can be done. Tip can be used to manipulate the surface sample. It can be used to write the features. It can be used to scratch the certain region. It can use to take one atom from one place to other places or bring one atom to other any places to put. So, such kind of manipulation can be done at the atomic level using a scanning tunneling microscope or using a atomically sharp tip. As per the tunneling spectroscopy is concerned or scanning tunneling spectroscopy is concerned, we have we can go for IV spectroscopy or IZ spectroscopy. I is certainly tunneling current, V is the bias voltage, and in other cases I is the tunneling current and Z is the distance between the tip and sample. As per the IV spectroscopy is concerned, the electrons tunnel from the tip to sample, that means it goes via the gap between the tip and sample, and that gap can theoretically be a real gap. The gap may be air, may be vacuum, or may be some objects, very thin oxide layer can be there, or can be some molecule is there between the tip and sample, because I can bring one molecule in my tip and make it to touch on the surface, then that molecule will be on between the tip and a surface. This can all be done. Now, if in previous cases in imaging process, what we do, we put the tip at a constant height mode and measure the current, and that current we use for imaging purpose. And when we measure the current, the bias potential remains constant. Bias potential is either 0.1 or 0.5 or up to 1, like 0.1 to 1 volt is used as a bias potential between the sample and tip. So, bias potential is kept fixed and we measure the current between the tip and sample while moving the tip or scanning the tip on the sample, that is in constant height mode. In other cases in constant current mode, our tip goes up and down. Again there is a bias potential that is fixed. Tip goes up and down, and that tip goes up and down because of different bias, different potential given to the piezo scanner, and that voltage is utilized for image construction. But in the IP spectroscopy, what we do actually, we keep a constant distance and then change the voltage and see how the current or tunneling current is varying with the voltage, bias voltage between the tip and sample. So, it can it is done mostly in a local one place. First you the tip stay at one place and you measure the current by changing the bias voltage, or it can also be done in the scanning, during the scanning, that can also be done. This is not unusual, that can also be done. And now, when electron tunnel between the sample and tip, it may lose energy or may not lose energy. Now, if it do not lose energy, if the energy of the electrons remains same when it goes from the tip to sample, that is a elastic spectroscopy or elastic process we say. With that process we can measure the conductance, that means surface conductance across the sample. We can do it di by dB, we can get di by dB to get local density of states and also electronic structure. And second one is inelastic. Now, the electrons which comes or tunneling current, the electrons which is tunneled between the tip sample, that can be utilized that can be utilized for some other excitation process, like if a molecule is there and molecule has a vibrational level, if the energy of the electrons is good enough, then it can change the vibrational level, or it can do an excitation in the molecule between present between the tip sample, and then if the energy of the tunneling electrons changed because it is utilized for a process, then it is called inelastic, and this provide vibrational spectroscopy. So, we are not going to discuss on the inelastic or vibrational spectroscopy, but mostly we will concentrate on the elastic or IV spectroscopy, particularly the conductance measurement and dI by dV measurements. We can do the local work function because sample may not be uniform, or sample may be flat, but different region can be have different material, different sample, and therefore their work function will be different, and as their work function will be different, that is nothing but barrier height will be different. So, using this scanning tunneling spectroscopy, we can measure the work function at different location of the sample. So, this is done by varying the voltage to the piezo scanner. Here a sinusoidal modulation of voltage is given to the piezoelectric device attached to the tip. So, when a sinusoidal voltage is given to the piezo scanner, that will make tip up and down. So, it will go like that. So, therefore, let us say we give a voltage Vt to the tip. Actually, voltage is not given to the tip, but voltage is given to the piezo scanner, because when we give the voltage to the piezo scanner, then only the height changes. But as we are giving the voltage, as the tip is attached to the scanner, therefore, I am writing Vt, which is equal to V0 initial voltage plus Vm, let us say sin omega t, omega is the frequency. Now, by giving this voltage, the distance between the sample and tip will change. That means, there will be del z del z0 plus del zm sin omega t. This can be done. Here, this del zm and Vm are related to the piezoelectric coefficient. We have discussed earlier piezoelectric coefficient. I am not going to again go with those things, and accordingly, as it is oscillating voltage and oscillating change of the height, or the del z is changing, there will be a oscillating tunneling current, which can be written as I t, which is equivalent to like I 0 V e to the power minus alpha root over of phi del z 0 phi root over of phi only, then del z 0 plus sin omega t. Sin omega t. This is one, and where this alpha is nothing but 2 cross h root over of 2m, which is can be the amplitude of tunneling current, amplitude of the tunneling current can be will be proportional to I omega I 0 to d33, this is a piezoelectric coefficient, Vm divided by h cross root over of 2m phi phi r x y. So, this is what the amplitude of the currents we will get it, and from that we can get the information about the work function of the sample across the xy direction. In this way, we can measure the work function of the sample at each point on the specimen along with the topography of the sample. And that work function can also be utilized for constructing a image, that is a work function image, that can also be done. This is one of the tunneling spectroscopy technique, and therefore, by doing that we can, like, different region have different work function. You can see a work function of one type of work function here, another type of work function here. So, work function mapping can be done by measuring the tip sample oscillation between the tip sample oscillation of the tip and measuring the amplitude of the current changing, and from that we get the work function. Another important things that we measure here is the current voltage characteristic. Here the voltage is varied. Voltage means for a short time we keep the tip sample at a fixed position and we stop here. Feedback controller is for a short time inactivated, and then we apply a bias difference and measure the current. By varying the bias voltage between the tip and sample, we measure the current, and from the IV graph we get the conductivity. In addition to that, that can be also used for local density of states. Particularly this type of measurements is done in ultra high vacuum condition, because to get accurate information about the surface atoms without any other surface adsorbent being absorbed on the surface of the atoms in a normal ambient condition, because if some of the moisture or some other things get adsorbed on the specimen in ambient condition, then we actually be measuring those adsorbents information instead of the real sample information, getting the real sample information. So, here is like simple metal contacts can be done, like tip and sample are both metals. Then you can see the ohmic behavior as you see the graph, IV graph. Similarly, for metal semiconductor, how you will see IV graph, all these kinds can be done with this. But the importance is that this type of measurements is also normally very conventionally done in the research or in the measurements, but here measurements is done through a single atom. So, you get information about the single atom only, a very local region, not like the average or all some whole area information. In order to get the whole area information, you have to do multiple places to get an idea, but actually doing the multiple places also not sufficient enough to get throughout the region what is happening. But in case of nanomaterials, or in case of getting information for specific site, specific position, scanning tolerant microscopy is most suitable. In addition to IV measurements, one can do also di by dV measurements, that can simply be done by mathematical differentiation, but actually in the scanning tolerant spectroscopy it can be measured directly using a lock-in amplifier, because that gives better signal to noise ratio. So, in the di by dB measurements, the voltage which is given to the sample, that is a small sinusoidal modulation of the voltage is given to the sample, and then this type of sinusoidal voltage is added to the DC bias applied to the sample, and this output again will be in these cases again del I sin omega t r, output will be like this, and this modulation of the current it is given to the lock-in amplifier as a reference, and other one will come as a V input, and providing the V lock-in will be equal to the output from lock-in amplifier will be equal to like minus di by dV del V cos phi. There will be a component, this is a phase difference component between the input and reference voltage. Phase difference, it can be made, cos phi can be made to 1. So, in these cases, if we make the del V to be constant, then we can see how the lock-in amplifier, lock-in this V lock-in is proportional to the di by dV. So, this di by dV data can be utilized for the spectroscopic purpose to measuring the local density of states, and how it looks like is that here di by dV measurements providing here di by dV measurements versus voltage. You can see the occupied orbitals here, unoccupied orbitals. So, this is nothing but providing also a band gap of the sample, giving the energy gap or forbidden gap of the sample. This type of density of states also done by measuring by plotting di by dV versus I by V. So, this type of plot is also done. One can get this type of plots. These are nothing but the energy gap or the gap between unoccupied and occupied levels of the surface atoms, or thus it is giving the local density of states. Here is an example how this type of spectroscopy is utilized for studying the nanomaterials, because conventional technique cannot be utilized for measuring the IV characteristic of features that are very small, particularly with an example of carbon nanotube. It can be described much easily. As you know, the carbon nanotube is nothing but a rolled up graphene sheet. So, it can be rolled in different angle, providing different type of carbon nanotube, that is called chiral nanotube, and those some of the, depending upon the rolling angle, it can be semiconductor, it can be metallic. So, those kind of study can be studied, like whether a carbon nanotube, single wall carbon nanotube is a metallic nanotube, or it is a semiconducting nanotube, that can be studied exclusively by scanning tunneling microscope, because all other techniques available cannot be utilized to pinpoint one single nanotube and study its electronic structure, and also its band gap, etc. So, in this particular cases, what we see here, this is a graphene sheet. This is a graphene sheet which have hexagon hexagons, and depending upon their that can be zigzag. The zigzag nanotube have we know the chiral vector CH is equal to NA1 plus MA2. So, A1 A2 are vector and NM are the integers, and if it is M is 0, in this cases as you see M is 0, it is a zigzag nanotube, and if N is equal to M, then it is a armchair nanotube. In case of this is armchair nanotube, armchair, in this cases armchair like 3 3, the vectors 3 3, 4 4, these are like armchair tube, or 5 5, these are armchair tube. On the other hand, if 1 0 2 0 3 0 4 0 like that, then we have zigzag tube, and depending on the rolling we can also know these are armchair tube or these are zigzag tube. As you see here, there are different tubes, STM image is taken, and here we have a tube axis, and now when it is rolled up, this is rolled up with this dash line and this dash line, and as you see when it is rolled up, how these hexagons are at a particular angle of phi from the tube axis, that is called chiral angle, and in this one type of tube, like say tube number 10, and this chiral angle is 7 degree. That means from the tube axis, this is tube axis to this edge vector axis, edge axis, we can have 7 degree. Now, one can actually measure this how these hexagons are aligned along the tube axis versus tube axis, because these darker places are the middle of the hexagon, like as it mentioned here, and the brighter portion are the atomic positions of the carbon atom. In this way, the chiral angle can be measured. From the chiral angle, it can be known whether it is a chiral tube or a armchair, and this is like a armchair tube, this is like a zigzag tube, one can measure. This measurement was done with a bias voltage of 0.5 millivolt with a 60 picoampere of current. So, now using the tip, we can bring the tip to, close to the one nanotube, one such nanotube, and then measure I versus V. And by measuring the I versus V curve, as you see here how the I versus V curve is being seen. In case of chiral tube, there is a low conductance, then it keep on increasing with several kinks etc., giving rectifying behavior. On the other hand, you see the armchair going is like showing a ohmic behavior, IV characteristic going in the linear fashion, unlike other tube which are showing the non-linear type of IV curve. And this indicates that armchair, this particular armchair number 8 is metallic in nature. And normally one can know that this nanotube are metallic or not, but if n minus m divided by 3 is an integer, then it is a metallic tube. Integer, then it is metallic. So, one can actually measure such kind of information whether it is a metallic tube, semiconductor tube using this scanning tunneling spectroscopy. And this is a di by dB data in the right side. Here you see a di by dB data versus voltage, and it gives the band gap, energy gap are in the range of 0.55 or 0.5 to 0.6 volt in the range. This is the energy gap. These are the density of states. In addition to that, there is also secondary gaps because of other region which is beyond the scope of this lecture. But this di by dB versus voltage can be utilized to measure the band gap of or electronic properties of the single wall nanotube or single features which are very small in size. Here is an example of nickel gold system. This is shown in as an image how the local density of states changes across the sample. Now, what we can see in the left side, there is three type of contrast. One is very bright, like this region and this region are very bright, and this region even more bright, and this region is a dark, this region dark, this region dark. Around the darker portion there is a brighter atoms. These are all brighter atoms. So, A is a nickel with 2% gold, nickel with 2% gold. Here these darker portion are nothing but the gold. AU atom appears depression because of the local density of states, local density of state at the Fermi level, because AU appear as a depression because at that places the density of state is lower, there is unoccupied states. As at unoccupied states, enough electrons is not available. As enough electrons is not available, we are measuring a very small current there or almost no current. So, as we are measuring no current, then therefore, those regions are appearing the darker. But interestingly, what we see also another feature, that around that gold atom, nickel atoms are more brighter. Here all are nickel atom, these are all nickel atom, but the nickel atom which are present around the gold atom are far brighter. That means, the nickel atom surrounding the gold atom appears protrusion because of the enhancement of the local density of states. Because so, indicating their higher chemical reactivity, that those nickels have reacted with the gold in a manner that they have changed itself and their density of states goes higher. Therefore, the atoms which are close to the gold atom, they are not only they are not the normal nickel, but rather they undergo some changes. Therefore, they are showing a much higher density of states. And in the second B1, this is a 7% gold atom, number of nickel atoms enhanced, as that therefore, you see quite a large number of such gold atom, because number of gold atoms is much higher. So, around all the dark region, around all the dark region, we see the brighter nickel atoms. So, it indicating that how the atomic reactions is occurring at the atomic levels. So, all the nickel atom around the golds have changed due to certain chemical reaction, and therefore, their electronic properties has changed. This type of chemical reactivity at the atomic level can only be studied by scanning tunneling microscope. There is no other technique available which can provide this type of information. Second thing, we can also change the bias voltage. This is also I have discussed in the last class. So, bias voltage we can change when if the sample is biased negative, we can make the sample to be biased as negative. As you know, we always bias the sample, not the tip. Tip is grounded. If the sample is biased negative, then we can get the information about the field electronic states on the surface atom. So, field electronic states of the surface atom, because electrons will tunnel from the field states of the specimen of the sample to the tip. On the other hand, when the sample is biased positive and tip is grounded, so that electrons will tunnel from the tip to the unoccupied states or empty electronic states on the surface atom. So, in this way we can get the information about the occupied states or unoccupied states of the sample specimen by providing the either positive or negative bias to the sample. So, here this is what I have shown before. When sample is given a negative bias, then electrons will tunnel from the field states of the sample to the tip. On the other hand, if the sample is biased positive, electrons will tunnel from the tip to the unoccupied states of this specimen, giving, and in these cases we get STM image of unoccupied states. But on the other hand, here we get STM image of occupied states of surface atoms. So, this is the importance of applying the bias voltage. Here is an example, the silicon 001 surface. What we can see here, that you see that is 1 surface. Here sample is biased negative. When sample is biased negative, it gives the occupied states information of the surface atoms. So, now you can see they are all dimers, 2 silicon atoms. Now, these are giving occupied states information. Both are brighter because the electrons is tunneling from the occupied states of the sample or silicon to the tip. On the other hand, at positive bias, positive potential, it is doing opposite. The electrons is going from the tip to the sample, unoccupied states. So, at positive voltage, most of the tunneling current is carried through the pi unoccupied portion of the local density of states. So, we know in case of dimer, we have the sigma bond is very strong, it is low energy. As it is low energy, electrons do not tunnel from those low energy levels, but we have pi and pi star. So, pi star is occupied and pi star is unoccupied levels. So, in these cases, particularly for applying when we want to study the unoccupied states, by applying the sample as a positive potential, electrons will tunnel to the pi star or occupied states or empty states. Therefore, as electrons is tunneling to the empty states, therefore, in this region we will see the low current, or it will see as a darker. So, the region where it is brighter, this is higher current, tunneling current compared to the other region. So, in this way the sample is same, surface is same, but now we are getting how the unoccupied states are arranged on the surface atoms and how occupied states are arranged on the surface atom by changing the bias voltage or polarity of the bias voltage. So, in conclusion, what we have seen that scanning tunneling spectroscopy is used for getting a surface electronic structure of the sample. It can be utilized for sample measuring work function and also getting the data of dI by dP, and those dI by dP data can be utilized to get surface electronic structure, including the band gap of the material of at the atomic level or very small size region where few atoms are there. This can be done. These are the references. Thank you.